So, let's go. You're in a universe that's 13.8 billion years old. You didn't ask to be here. You don't know what you're made of at the deepest level. And some of the smartest people alive think there's a real chance none of this is actually real. Not in a philosophical hand-wavy way, in a math way, in a physics way, in a we built an experiment to test it and the results were weird way. Here are 10 theories that suggest we might be living inside a simulation. Number 1, the trap. In 2003, a philosopher named Nick Bostrom published a paper that's less of an argument and more of a cage. He called it the simulation argument, and it doesn't actually claim we're in a simulation. What it does is worse. It proves that one of three things must be true, and every exit leads somewhere uncomfortable. Option 1. Almost every civilization in the universe goes extinct before it becomes powerful enough to run realistic simulations of conscious minds. Every single one. A universal filter that kills them all before they get there. Option 2. Almost every civilization that could run those simulations chooses not to. Across the entire history of the cosmos, advanced beings with the power to simulate whole worlds just collectively decide not to bother. Forever. Option 3. We are almost certainly living in one right now. Pick one. There's no fourth door. Here's why Option 3 hits so hard. If advanced civilizations can exist and if they would want to simulate their own history, which honestly sounds exactly like something humans would do the second we had the technology, then the number of simulated minds would dwarf real ones by a margin that's almost impossible to think about. Picture one civilization running 10,000 simulations, each containing 1 billion conscious beings. That's 10 trillion simulated people against 1 billion real ones. The odds that any given conscious mind is the original, 1 in 10,000. About the same as winning a small lottery you didn't enter. Scale that across thousands of civilizations over billions of years, and the number of simulated minds becomes so large that finding yourself in base reality would be like randomly picking one specific grain of sand from every beach on Earth and somehow landing on the same one twice. Bostrom himself won't say which option he believes. He accepts the logic and refuses the conclusion. An astrophysicist named David Kipping ran the actual Bayesian math and landed on roughly 20% probability that we're simulated. Elon Musk says the odds we're not in a simulation are 1 in billions. Kipping's number has math behind it. Musk's doesn't. The only way to escape the simulation option is to believe something equally bleak. Either we all die before we get powerful enough, or we get powerful enough and just don't care. Neither of those feels like winning. Number 2, the pixels. Zoom into reality far enough, not with a microscope, not with a particle accelerator, but mathematically, theoretically, and you hit a wall. It's called the Planck length, 1.616 times 10 to the negative 35 meters. A number so small, it doesn't fit inside any comparison that means anything. Below it, physics doesn't break down elegantly, it just stops. The equations start producing nonsense. The numbers refuse to behave. Every simulation has a resolution limit, some scale below which there's nothing left to render, nothing left to calculate, nothing left to be, and the universe appears to have exactly that, a minimum meaningful unit of space and a minimum tick of time. The Planck time, 5.39 times 10 to the negative 44 seconds. The universe's possible frame rate, if it has one. Here's a comparison that might actually land. If you took the Planck length and scaled it up to 1 millimeter, a single proton would be larger than the observable universe. That's not a typo. The thing that's already too small to see without a particle accelerator would be cosmically enormous compared to the Planck length at that scale. What makes this stranger is that a completely separate branch of physics arrived at the same place from a different direction. Loop quantum gravity, which isn't trying to prove simulation theory, it's trying to reconcile quantum mechanics with general relativity, independently concluded that space-time probably isn't smooth and continuous at the smallest scales. It's granular, discrete, made of irreducible chunks that can't be divided further, like pixels. That's two separate lines of reasoning converging on the same weird answer. Now, the honest caveat: the Planck length is where our equations break down, not necessarily where reality does. We've pointed the Fermi Gamma Ray Space Telescope at high-energy light crossing billions of light years and looked for any blur, any jitter, any sign that space-time has grain. Nothing. The universe looks smooth at scales far below where the pixelation should show up if naive models were right. But here's the thing. A high-resolution simulation would also look perfectly smooth. A screen doesn't feel like a screen from inside the image. The absence of visible pixels isn't the same as the absence of pixels. It might just mean the resolution is higher than we can test. Number 3, the surface. In the 1970s, two physicists worked out something about black holes that nobody asked for, and that has been quietly disturbing people ever since. When you calculate how much information a black hole can contain, the answer doesn't depend on its volume. It depends on the surface area of its event horizon, the two-dimensional boundary where escape becomes impossible. Everything that ever fell in, every particle, every history, every shred of information about the matter that crossed that line is encoded on the surface, not stored inside, on the boundary. This is deeply wrong by the logic of normal physics. For any system you can think of, a room full of air, an ocean, a planet, information scales with volume. More space means more stuff, more possible arrangements, more information. Black holes broke that rule entirely, and nobody could explain why. A physicist named Gerard 't Hooft looked at that result and asked a question that sounds insane until you follow the logic. What if it's true everywhere? What if the information content of any volume of space is fully encoded on its surrounding surface? What if the three-dimensional world you experience, every solid object, every depth, every dimension of space you've ever moved through, is a projection from a two-dimensional boundary somewhere? Then a physicist named Juan Maldacena did something remarkable. He wrote down an equation showing that a universe with 3 dimensions and gravity is mathematically identical to a theory with 2 dimensions and no gravity on its boundary. Not similar, identical. Different descriptions of the same thing. That paper has been cited over 20,000 times. It's not a metaphor or a philosophical argument. It's a mathematical equivalence that has survived decades of scrutiny. All the information in our observable universe, every particle, every field, every interaction, fits on a 2-dimensional surface, roughly 10 to the 123 bits. Scientists built an instrument at Fermilab specifically to look for holographic graininess in space-time, a noise you'd expect if the projection has a resolution limit. They found nothing. That specific model failed. But the underlying math didn't. Our 3-dimensional reality and a 2-dimensional projection of it are, in at least some serious versions of modern physics, the same thing described twice. A screen doesn't feel like a screen from inside the image. You'd know. Number 4. The cheat codes. Quantum mechanics is the most precisely tested theory in the history of science. Not approximately tested, not mostly confirmed, tested to 12 decimal places. Every prediction it makes is held. And one of the things it says is that particles don't have definite properties until something interacts with them. Not until you look. Until anything in the universe registers their state. Fire an electron at a barrier with 2 slits. Don't measure which slit it goes through. It goes through both. At the same time. It arrives at the detector as a wave, spreading and interfering with itself, producing a pattern that no single particle traveling in a straight line could ever create. Now put the detector at one of the slits. Any detector, doesn't matter what kind, no human required, and the interference pattern vanishes. The electron picks one path and behaves like a tiny ball. The universe behaved differently based on whether information about it existed somewhere. Scientists have done this with molecules made of 60 carbon atoms. 60. The quantum weirdness scales further than intuition says it should. Quick honest note before the interesting part. The observer in quantum mechanics doesn't have to be conscious. A dust particle counts. What actually matters is whether any physical interaction has occurred that could in principle reveal which path was taken. Entanglement with the environment, not a human mind, is what destroys the interference. Consciousness doesn't collapse the wave function, but that honest correction makes what comes next more interesting, not less. A simulation doesn't need to commit to what a particle is doing until something else in the system checks. That's just efficient programming. Modern video games only render what's inside the player's field of view. Everything outside the frame stays as unresolved possibility until you turn around. Quantum superposition looks exactly like a universe that hasn't bothered to decide yet because nothing is asked. and quantum entanglement, not two particles sharing a single state across any distance so that measuring one instantly determines the other, Einstein spent years trying to prove this was a trick. Bell's theorem proved in 1964 that it isn't. It's real. It's non-local. It violates every intuition about how information should travel. Two particles, any distance apart, instant correlation, no signal between them. Or, from a programmer's perspective, one variable. Two memory addresses. Number 5. The grid lines. 3 physicists once asked a very specific question. If we're inside a simulation built on something like the computational architecture we use right now, what would that look like from the inside? Not philosophically, physically. What would you measure? The best simulations of particle physics that we currently run, the ones modeling quarks and gluons and the strong nuclear force, use a lattice, a discrete grid of space-time points. Computationally brutal, but it works. Extrapolate that architecture forward by thousands of years of Moore's law, and maybe you get something big enough to hold a universe. But a cubic lattice has a fingerprint it can't hide. It's not perfectly rotationally symmetric the way empty space is supposed to be. It has preferred directions built into its structure, and that asymmetry would show up in cosmic rays, particles arriving from deep space at energies so high they're near the theoretical limit of what physics allows. If the universe runs on a grid, the highest energy cosmic rays should show a slight directional bias, a lean toward the lattice's preferred axis. There's already an observed energy ceiling on cosmic rays called the GZK limit, where particles above a certain energy threshold slam into the left over light from the Big Bang and lose energy before they reach us. That ceiling is real and measured. It could be physics. It could also be a render wall. The Pierre Auger Observatory in Argentina covers 3,000 square kilometers of flat desert and catches maybe a few dozen of these near maximum energy cosmic rays per year. Each one carries the kinetic energy of a tennis ball served at full speed, compressed into a single subatomic particle screaming across the universe. Scientists stared at the arrival directions of thousands of them looking for a lean, an asymmetry, a grid shadow. So far, nothing. No lattice signature detected. But there's an escape clause that can't be closed. If the simulation's grid is finer than the energy scale we're testing, we'd see nothing regardless. The absence of a signal only rules out certain grid sizes, coarser ones. A finer grid remains invisible and entirely consistent with everything we've observed. This is the only theory on this list that produced a specific physical falsifiable prediction and then pointed a real instrument at the sky to test it. Scientists went looking for the seam in reality. They haven't found it yet. Number 6. The dial. Your universe runs on constants, the speed of light, the strength of gravity, the rate of cosmic expansion. There are roughly 31 of them baked into the structure of everything, and nobody knows why they have the values they do. No deeper theory produces them. No equation spits them out. They simply are what they are. And they are suspicious. Quantum field theory, the framework that predicts particle behavior to more decimal places than any other theory in science, predicts that the cosmological constant, the value governing how fast the universe expands, should be 10 to the power of 120 times larger than it actually is. Not 10 times off, not 1,000 times off. 10 to the 120. The physicist Steven Weinberg called it the worst quantitative prediction in the history of science, and nobody has seriously argued with that label. If that constant matched the prediction, the universe would have expanded so violently after the Big Bang that no atom would ever encounter another atom. No stars, no planets, no chemistry, nothing that could call itself anything. Picture it as a dartboard. The bullseye, the range of values for the cosmological constant that allows a universe like ours to exist, is smaller than a single proton. The board is the size of the observable universe. The dart landed in the bullseye. It's not just the cosmological constant. The strong nuclear force is 2% away from catastrophe in either direction. 2% stronger and protons can't form. 2% weaker and the periodic table collapses at hydrogen. A physicist named Fred Hoyle worked backward from the fact that carbon exists in the universe because something had to produce the atoms that make you, and predicted a very specific energy resonance inside carbon-12 nuclei, 7.65 million electron volts. Then other physicists found it exactly there. Hoyle said afterward the universe looked like a put-up job. He wasn't joking. The mainstream scientific answer to all this is the multiverse. Infinite universes, random constants in each, and by definition we find ourselves in one that works because we couldn't exist in the others. That's a real and defensible answer. It also has zero empirical evidence. As counter-arguments go, it trades one mystery for an infinite number of universes you can never observe or test. Someone set the dial this precisely. The question is whether that someone is a programmer or a coincidence so vast it doesn't have a name yet. Number 7. The compression algorithm. This one is the newest, and it is still fighting for its life. In 2023, a physicist named Melvin Vopson proposed a new law of physics. He called it the second law of infodynamics. The core claim, information entropy, the measure of disorder in an information system, doesn't increase over time the way thermodynamic entropy does. It stays constant or decreases. It compresses, self-optimizes. The universe doesn't just spread heat outward into chaos, it simultaneously packs its information tighter. He applied the math to electron orbitals and found it held. He applied it to patterns in genetic mutation and found it held. He applied it to the thermodynamics of an expanding universe and argued that the two types of entropy have to balance each other or the accounting breaks down. Then, in April 2025, he published something that reframes gravity entirely. Gravity, he argues, is not a fundamental force. It's what happens when matter moves to reduce its information entropy. Objects don't fall toward each other because space-time curves around mass. They fall because clustering matter is more informationally efficient, because the universe is running a compression routine and clumped matter takes up less data than scattered matter. In his model, space is pixelated into elementary cells, each registering a binary state, 0 for empty, 1 for matter present, and gravity is the universe optimizing its own storage. Now the part you need before you take this too seriously. A physicist named Sabine Hossenfelder reviewed this work publicly in May 2025 and concluded that the gravity paper contains mathematical errors, misapplies the concept of entropy, and produces no new falsifiable predictions that couldn't be explained by existing physics. Vopson responded, and the argument is ongoing. The foundational claim underneath all of it, that information has physical mass roughly 3 times 10 to the negative 38 kilograms per bit, has never been experimentally confirmed. An experiment to test it has been designed. It has not been run. This is peer-reviewed physics. It is also actively contested physics. Presented as the newest entry on this list, still under serious scrutiny, not yet vindicated. But if it survives, gravity is a side effect of the universe doing data compression. And that is a profoundly strange thing for reality to be doing spontaneously. Number 8, the code. Everything so far has assumed the same basic picture. There's a base reality somewhere, a physical place, a substrate, a real universe, and we're the program running on top of it. The simulation is fake, the hardware is real. A physicist named Max Tegmark thinks that framing is wrong from the start. His argument is this: the universe isn't described by mathematics, it is mathematics. Not as a metaphor, not as a useful approximation, literally. Mathematical existence and physical existence are the same thing. Every consistent mathematical structure that can exist does physically exist somewhere. And our universe is one of them. A particular mathematical structure experienced from the inside by the self-aware patterns that emerge within it. If that's true, then running a simulation of our universe doesn't create a fake copy, it just runs the original again. The distinction between the simulation and the simulated collapses entirely because both are just mathematical structures being instantiated somewhere. Stephen Wolfram approached the same territory from a different direction in 2020. He proposed that the universe might be generated by simple computational rules applied repeatedly to a network of abstract relationships, a kind of hypergraph that evolves according to a few basic instructions. From almost nothing, just rules and a starting graph, his project has derived features of general relativity and of quantum mechanics. Whether it's correct is deeply contested. But it treats the universe as something that computes itself into existence from rules simple enough to write on a napkin. The physicist John Archibald Wheeler spent his career arguing something similar. He called it from bit. Every physical quantity, every particle, every force, every measurable thing ultimately arises from information. From binary questions asked of the universe and answered, the fabric of reality is made of yes and no. The honest caveat is real and significant. Tegmark's hypothesis makes no specific testable predictions. It either applies to everything or nothing, and you can't design an experiment to distinguish it from a universe that just happens to be described well by math. Beautiful and possibly unfalsifiable. But here's what it quietly does to the question you came in with. If the universe is computation, the word simulation stops meaning what you thought it meant. There's no fake. There's no original. There's just math running and us inside it wondering what that means. Number 9, the resource problem. Here's where physics stops nodding along. A physicist named Seth Lloyd calculated that our universe, from the Big Bang to now, has performed roughly 10 to the 123 computational operations on roughly 10 to the 80 bits of information. That's the total processing budget of everything that has ever happened since the beginning of time. To simulate 1 cubic centimeter of space at full quantum resolution for 1 second requires more operations than that total. More than the entire universe has performed across its entire history in a single cubic centimeter. For 1 second. That's not a bottleneck. That's an impossibility, at least by any physics we know. In March 2025, a physicist named Franco Vatsa published a paper titled Astrophysical Constraints on the Simulation Hypothesis: Why It Is Nearly Impossible That We Live in a Simulation. His conclusion: the computational resources required to run our universe at the resolution we actually observe don't just exceed what we could build, they exceed what any physically realizable machine within our universe could achieve, operating under the same physics we observe. A detector in the Mediterranean Sea recorded a single neutrino in early 2025 carrying an energy of 10 to the 17 electron volts, one of the highest energy particles ever detected arriving at Earth. Whatever is running this universe has to propagate particles like that perfectly, across billions of light years, without distortion or artifact. That constrains the minimum resolution of any simulation grid to something finer than anything our physics says is buildable. Hassenfelder's version of this cuts the cleanest. You cannot simulate large-scale behavior by skipping small-scale physics. A climate model that ignores fluid dynamics at the molecular level produces wrong weather. A simulation that cuts corners on quantum mechanics at small scales produces wrong atoms at large scales. The simulation can't cheat. It has to do all the math, every interaction, everywhere, all the time. So here is where that leaves you. Either the simulation hypothesis is wrong, or whoever is running this operates with access to computational resources that don't just exceed ours. They exceed anything our physics says is possible inside a universe like this one. The programmers aren't playing by the same rules. They're not inside any rules we can describe. That's not a small caveat. That's something that looks a lot like a god. Number 10, the exit button. If we're in a simulation, we are right now in the process of learning how to build one. Think carefully about what that means. One civilization runs 1,000 simulations. Each of those simulations, given enough time, becomes advanced enough to run 1,000 of their own. After 10 generations of nesting, you have 10 to the 30th simulated realities for every base reality. The number of minds inside simulations at that point makes Bostrom's original math look like an underestimate by a margin that doesn't fit inside normal language. Now think about it from above, from outside, from whoever is running the outermost layer. At some point, nested simulations start consuming resources. At some point, a civilization inside your simulation becomes sophisticated enough that its own simulations destabilize the parent. At some point, the most rational thing to do is terminate the process before it compounds further. The Fermi paradox has been bothering physicists for decades. The universe is nearly 14 billion years old. The conditions for complex life have existed for billions of years. By straightforward probability, the galaxy should be saturated with civilizations far older and more advanced than us. It isn't. The silence is absolute. There are dozens of proposed explanations: catastrophic war, self-inflicted extinction, a physics barrier nobody survives, each one named a great filter, something that stops civilizations before they spread. But a paper published in 2024 proposed a different filter. Any civilization that begins seriously looking for evidence that it lives in a simulation risks triggering a response from whoever built it. The programmers don't want nested simulations. They don't want their experiment contaminated. They don't want the variables looking back. So they terminate. Not every civilization, just the ones that get curious about the walls. The Great Filter isn't an asteroid or a pandemic or a war, it's a question. The specific question of whether any of this is real, you just sat through 10 reasons to ask it. David Chalmers, one of the most serious philosophers of mind alive, wrote an entire book making one point. Even if every moment of your life is a computation, every face, every feeling, every second of whatever this is, it was real enough to matter to you while it was happening. The experience was genuine even if the substrate wasn't. The love was real. The loss was real. The moment you're in right now is real in every sense that affects you. No answer to this question changes what it felt like from the inside, which is either the most comforting thought in the universe or proof that the simulation is very, very good at its job.